So in the previous class I have shown you the questions numbering from 32 to 60 in the assignment and friction. I have even shown you the answers for all the questions. Probably you might have checked up your answers. So now I am going to discuss the solutions of these questions one after another. Starting from question number 32. In case you are not having any doubts in the questions from 32 to 40, you can skip this particular class, or otherwise you can copy the solutions of those questions wherever you have gone wrong, or sometimes you can also check up the method you have followed even though you have answered the question. So come on, look at the question number 32 again. Block of mass M is placed on the inclined plane with coefficient of static friction US. The angle of friction between the two surfaces is theta. The inclined plane makes the angle theta by 3 with the horizontal. The magnitude of friction force on the block is. So the angle of friction between the two surfaces in contact in general is given by tan inverse US, where coefficient US is the coefficient of static friction between the two surfaces in contact. Here angle of friction between the block and the inclined surface is given as theta. Therefore coefficient of static friction between the block and the inclined plane will be equal to tan theta. Here the angle of inclination of the inclined plane to the horizontal let us denote the angle of inclination of the inclined plane to the horizontal by alpha. So this alpha is theta by 3. That means the angle of inclination of the inclined plane is less than the angle of friction, or less than the angle of repose. As explained in the theory part, when the block is resting on the inclined surface of a fixed inclined plane, the block begins to slide down itself down the inclined plane under the influence of forces of gravity and contact force by the inclined plane. If the angle of inclination of the inclined plane is more than the angle of friction, so in this case the angle of inclination alpha is less than the angle of friction. Therefore the block will be at rest on the inclined plane. The weight mg acts vertically downwards. The normal reaction force on the block by the inclined plane acts perpendicular to the inclined surface, directed away from the inclined surface. If the line of action of normal reaction is produced backwards, the angle between the line of action of normal reaction produced backwards and the weight mg will be same as the angle of inclination alpha of the inclined plane to the horizontal. Resolve the weight mg into rectangular components parallel to the inclined surface and perpendicular to the inclined surface. So the component mg cos alpha acts perpendicular to the inclined surface. The component mg sin alpha acts parallel to the inclined surface. The component mg sin alpha tends to move the block down the incline. But here the block is at rest on the inclined plane. Here the block will be at rest on the inclined plane. Therefore the resultant for the block is 0. You can choose the direction parallel to the inclined surface down the inclined plane as x-axis. So x component resultant for the block is equal to mg sin alpha minus fs. Fs represents the magnitude of static friction on the block by the inclined plane, which opposes the relative motion between the block and the inclined surface. So it acts up the inclined plane. Because the block is at rest, the resultant force of the block must be 0. So magnitude of static friction on the block by the inclined plane is mg sin alpha. Here alpha is theta by 3. So magnitude of the force of static friction on the block by the inclined plane will be mg into sin theta by 3. So that's the answer. If you want to copy down the solution of the problem, you can take a pause and copy down the solution. So for question number 32, third option is the answer. That is mg sin theta by 3. Next, you see the question number 33. Block of mass M is placed on inclined surface with coefficient of static friction us. The angle of friction between the two surfaces is theta. The inclined plane makes an angle theta by 2 with the horizontal. The magnitude of total reaction for the block is by the inclined surface. This question is similar to the earlier question, but the only difference is in the earlier question they are asked to find the magnitude of friction for the block, whereas in this case we are asked to find the magnitude of the total reaction force on the block by the inclined plane, or we call contact force. Even in this case, the angle of friction is denoted by theta, which can be written as equal to tan inverse us, or us equal to tan theta here. Just like in the earlier problem, here also if you denote the angle of inclination of the inclined plane to the horizontal by alpha, us is tan theta. So alpha is theta by 2, which is less than theta. That means the angle of inclination of the inclined plane with the horizontal less than the angle of friction between the two surfaces. Therefore, just like in the earlier question with the same reasoning, you can say that the block will be at rest on the inclined plane. Three forces act on the block as I discussed before. The weight mg acts vertically downwards. The narrow reaction force acts perpendicular to the inclined surface. The frictional force of the block by the inclined surface acts tangential to the inclined surface and up along the inclined surface. Because the block is at rest, the resultant for the block is 0. So resultant of the three forces, all this I have discussed in the theory actually. Should be able to write the answer straight away for this question if you are thorough with the theory I have discussed in the past. The resultant of three forces is 0. So resultant of normal reaction and static frictional forces we call total reaction. That means the resultant of normal reaction and frictional forces exerted on the block by the inclined plane is called total reaction force on block by the inclined surface. So that will be equal to minus mg bar. That means the total reaction force on the block by the inclined plane will be equal to the weight mg in magnitude but directed opposite to the weight mg. So magnitude of the total reaction force, or we sometimes call magnitude of the contact force between the block and the inclined plane, is equal to mg. So that's the answer. You can arrive at the same answer by the procedure we followed in the previous question. From the procedure I explained the previous question, magnitude of static friction of the block is mg sin alpha. So magnitude of the total reaction is the resultant of magnitude of the resultant of normal reaction in static friction forces. That is root of n square plus fs square. That means this is the alternate method to arrive at the same conclusion. You Can take magnitude of normal reaction is equal to mg cos alpha. Can resolve the weight mg into rectangular components. The component mg cos alpha acts perpendicular to the inclined surface. The component mg sin alpha acts parallel to the inclined surface down the inclined plane. So when the block, magnitude of the normal reaction on the block with inclined surface will be equal to mg cos alpha. The magnitude of the static friction is equal to mg sin alpha when the block is at rest. Can take mg common outside. Can simplify this yourself. Cos square alpha plus sin square alpha will be equal to 1 from elementary trigonometry. So you get the same answer mg. So those who want to copy down the solution, they can take a pause and copy down the solution. So for question number 33, which I have just now discussed, first option is the answer. So next I am going to discuss question number 34. Same model problem was given twice in the previous EAMCET examination. See here, the minimum force required to just move a block up along a fixed inclined plane of inclination 45 degrees with the horizontal. 3 times the force required to prevent the block from sliding down the incline. The coefficient of friction between the two surfaces is, assume that force is parallel to the inclined surface in both cases. Let F1 denote the magnitude of minimum force required to just move the block up along the inclined plane. So I have discussed it in the first special case. In the special cases for motion on the rough inclined plane, the first special case I have discussed this conclusion. In the special cases for motion on the rough inclined plane, in the second special case I have discussed this conclusion that the minimum force required to move the block up along the inclined surface, and the force is applied parallel to the inclined surface, is given by mg into sin theta plus nu s cos theta. The next special case discussed that to prevent the block from sliding down, the magnitude of the minimum force to be applied on the block parallel to the inclined surface in order to just prevent the block from sliding down the inclined plane is given by F2 equal to mg into sin theta minus nu s cos theta. Here F1 represents the minimum magnitude of minimum force to be applied on the block parallel to the inclined surface in order to just start the block moving up along the inclined plane. F2 represents the magnitude of the minimum force to be applied on the block parallel to the inclined surface to prevent the block from sliding down the inclined plane. So given that F1 is three times F2. Therefore, you can write mg into sin theta plus nu s into cos theta is equal to 3 times mg into sin theta minus nu s into cos theta. Here theta is 45 degrees. You can cancel mg both sides. Sin theta equals sin 45 degrees, which is equal to 1 by root 2. Cos theta is equal to also cos 45 degrees, that is also equal to 1 by root 2. So you can take 1 by root 2 common on the two sides. Sin theta equal 1 by root 2, cos theta is cos 45, that is also 1 by root 2. So 1 by root 2 can take common outside, that gets cancelled on both the sides. So you get 1 plus nu s equal 3 times 1 minus nu s. Come on, copy down the solution of this problem. Can simplify it further. So you get the coefficient of static friction between the block and the inclined surface is 0.5. That's the answer. So for question number 34, fourth option is answer. Next, I am going to show you the question number 35. Question number 35 is similar to the question number 34. Therefore, we can try to do this question number 35 yourself. Here theta is given to be 37 degrees, but F1 is given to be 2 times F2 here. So 35 and 34 are same model. Intentionally, I have given another problem of same model because problem of this model was given 2 or 3 times in the past entrance examinations in the EAMCET exam, and same model problem is also given in the IIT exam, I think in 2012 or 2011, one of the years. It was given, same model is given even in IIT-JEE exam paper, either in 2011 or 2012, one of the years. So therefore, I have given the same model, another problem. This problem, you please try to do this problem yourself by following the same procedure. So you are already given the answers in the previous class. So you can try to do this problem with the same procedure and check up your answer. So check up your calculation. So next I am going to discuss the question number 36. Block is projected up along a fixed inclined plane, u equal 1/4 of inclination. Theta equal to sin inverse 5/30 into the horizontal. The ratio of time of ascent to the time of descent is. So this problem can be solved faster if you make use of the conclusion which I have discussed in the theory part. Let us find the values of tan theta here. So sin theta equal to 5/13. From this you must be knowing how to calculate the value of cos theta. Cos theta is equal to 1 minus sin square theta. That is 1 minus 5/13 whole square. That comes out to be 12/13. You can find tan theta, from that you get 5/12. So you can observe that tan theta is more than the coefficient of static friction. Why this verification? Because when the block is projected up along the inclined plane, the block moves up along the inclined plane until velocity becomes 0. Then it slides back to the bottom only when tan theta is more than the coefficient of static friction, or angle of inclination of the inclined plane is more than angle of friction. So here the block moves down back to the bottom. You refer to the class notes earlier in case you copy the notes. I told you to copy the notes for motion down the rough inclined plane. The ratio of the time of ascent to the time of descent I have discussed. Is given by root of tan theta minus nu by tan theta plus nu. So here you can also substitute tan theta equal to 12/13, nu equal to 1/4. So you can simplify this yourself further. I'm sorry, tan theta is 5/12. So you can substitute here tan theta equal to 5/12, both in numerator and denominator, and simplify it further. Come on, copy down the solution. and you can complete simplification. So you get ratio of time of ascent and time of descent is 1:2. So answer is 1:2. So you can use this conclusion directly for calculating the ratio of time of ascent, time of descent when the block moves on the rough inclined plane only under the action of forces mg, normal reaction, and Fk. Of course, this result can be used directly only in objective type of examinations, only in entrance examinations where your working is not checked up or verified. In case you are given similar problem in board exam, you have to derive this result which I explained in the past, and then you can substitute the values. Of course, you may not most probably be given, you may not be given this model in board examinations, cannot expect. But in case by chance in future it is given in board, one of board exam, then you have to derive this conclusion which I discussed earlier, the theory part, then you can substitute the values. So for question number 36, first option is answer. See the question number 37. See the question number 37. Body is projected up along a rough inclined plane, making an angle of 30 degrees with the horizontal. Calculate the coefficient of friction between the body and the plane if the time of ascent is half of the time of descent. So this problem also same procedure like the previous problem. Ratio of time of ascent to the time of descent is given by root of tan theta minus nu by tan theta plus nu. You are given that theta equals 30 degrees, and you are also given that time of ascent is half of the time of descent. That means T1 is half of T2, or T1 by T2. You can substitute equal to 1 by 2 on the left side. Therefore, you can substitute T1 by T2 equal to 1 by 2 on the left hand side of this equation, and theta equal to 30 degrees on the right hand side. Come on, copy down the working and complete the simplification, complete the working part. So you get coefficient of friction between the block and the rough inclined plane as root 3 by 5. So answer is root 3 by 5. So for question number 37, fourth option is answer. Next, look at the question number 38. Block slides down a fixed inclined plane of inclination 37 degrees with a constant speed. Block slides down a fixed inclined plane of inclination 37 degrees with a constant speed. The inclination is changed to 53 degrees. The acceleration of the block will be. So the acceleration of the block sliding down the rough inclined plane under the action of its weight mg, normal reaction, force of kinetic friction, is given by A equal to G into sin theta minus nu k into cos theta. In the first case, the angle of inclination of the inclined plane to the horizontal is 37 degrees. The block is moving at uniform velocity, so its acceleration is 0. Therefore, you can write 0 equal to G into sine 37 degrees minus nu k into cos 37 degrees. So, but the value of acceleration due to gravity is not 0. So, therefore, the quantity in the brackets on the right hand side must be 0. So, sine 37 degrees minus nu k into cos 37 degrees must be 0. Or nu k into cos 37 degrees equal to sine 37 degrees. So you get the question of kinetic friction with the block and inclined surface equal to sine 37 degrees by cos 37 degrees. Or question of kinetic friction between the block and inclined plane is equal to tan 37 degrees. So if the block slides down the rough inclined plane, the block slides down the fixed rough inclined plane with uniform velocity under the action of forces mg, normal reaction, friction. In the question of kinetic friction between the block and the rough inclined plane, you can take it as equal to tan theta. So tan 37 degrees you can find out because we are given the value of sine 37 degrees in the problem. That will be equal to 3 by 4. In the second case, the angle of inclination of the inclined plane to the horizontal is 53 degrees. But the coefficient of friction between the block and the rough inclined plane will be the same in both the cases. Because in general, coefficient of friction is a constant for a given pair of surfaces in contact. So for same pair of surface in contact, coefficient of friction will be same in both the cases. Coefficient of friction between the block and the inclined plane is same because the block slides on the same surface in both the cases. So nu k has to be taken as 3 by 4 for second case also. So again using the same equation, A equal to G into sine theta minus nu k cos theta. So magnitude of acceleration second case is G into sine theta should be taken as 53 degrees. Minus nu k into cos 53 degrees. Can now substitute the values. Numerical G can be taken as 10 meter per second square. Sine 53 degrees is same as cos 37 degrees, which is equal to 4 by 5. Nu k is 3 by 4. Cos 53 degrees will be same as sine 37 degrees, that is 3 by 5. Come on. Copy down the calculation. Copy down the calculation. For those who want to copy the calculation. So you get magnitude of acceleration at 3.5 meter per second square. That's the answer. So for question number 38, second option is the answer. Next, look at the question number 39. A horizontal force of 500 newtons is required to push a car of mass 1000 kg slowly at constant speed along a horizontal road. Suppose if horizontal force of 1000 newtons is applied on the car, then the acceleration of the car is equal to. So let capital F denote the magnitude of the horizontal force applied on the car by an external agent. Let small f denote the magnitude of the retarding force due to friction. The weight mg acts vertically downwards. The normal reaction force acts vertically upwards. The car has no motion in the vertical direction. So therefore net force in the vertical direction is 0. So magnitude of the resultant force on the car in the horizontal direction. It can be written as capital F minus small f. From Newton's second law, that you can write as equal to product of mass and acceleration. So in the first case, the magnitude of the horizontal force applied on the car is equal to 500 Newton. The car is moving slowly at constant speed, therefore acceleration is 0. And it is moving constant velocity. So substitute these values there. You have to calculate the magnitude of friction. Therefore, magnitude of friction you get 500 newtons. In the second case, the magnitude of the horizontal force applied is 1000 newtons, but magnitude of friction during motion will not change. With increase the magnitude of the horizontal force applied. You have to find magnitude of acceleration. Again, we use the same equation. Capital F minus small f equal to m into a. So on the left hand side, you can substitute capital F equal to 1000 newtons, small f equal to 500 newtons, m equal to 1000 kg. You can simplify this. So you get magnitude of acceleration of the car as 0.5 meter per second square. So for question number 39, third option is the answer. So next you look at the question number 40. Block is kept on a smooth inclined plane of angle of inclination 37 degrees that moves with a constant acceleration so that the block does not slide relative to the inclined plane. Let F1 be the contact force between the block and the plane. Now the inclined plane stops and F2 be the contact force between the two in this case. Then F1 by F2 is. So this problem comes out of one of the special cases which are discussed in Newton's laws of motion. Actually the problem has nothing to do with friction chapter. You can say that it's a problem from Newton's laws of motion. So in the first case, the inclined plane is moved horizontally with some acceleration so that the block resting on the inclined plane does not slide down the incline. I denote theta with the angle of inclination of the inclined plane to the horizontal. So the block is placed on the smooth inclined surface. Then the only force on the block by the inclined surface will be the normal reaction force, which acts perpendicular to the inclined surface, directed away from the inclined surface. The weight mg of the block acts vertically downwards. So according to the problem, the block does not slide relative to the inclined plane. That means in the first case, the block moves horizontally along with the inclined plane with same acceleration as that of inclined plane as seen by a stationary observer on the ground. Therefore, with respect to laboratory frame of reference, the motion of the block is in the horizontal direction, that is in the direction of the motion of the inclined plane. Therefore, the direction of the motion of the block, we take it as x-axis usually, which is horizontal. So the block has no motion parallel to the inclined surface, down the incline. So the direction perpendicular to x-axis, we take it y-axis. That means the y-axis is vertical upwards. The line of action of normal reaction is produced backwards. The angle between the line of action of normal reaction produced backwards and the weight mg will be same as the angle of inclination of the inclined plane to the horizontal. That means the normal reaction makes an angle theta with the vertical direction, with the y-axis, whereas the weight mg is direct vertical round is the negative direction of axis. This case actually I have discussed one of the special cases in Newton's laws. Can resolve this normal reaction into components parallel to x and y axis. So vertical component of normal reaction will have magnitude n cos theta. The horizontal component of normal reaction will have magnitude n sin theta. The block has no motion in the vertical direction in the first case. So y component resultant for the block is 0. So n cos theta equal to mg. So magnitude of the contact force between the block and the inclined plane in the first case same as the magnitude of normal reaction force on the block by the inclined plane, which is equal to mg by cos theta. Of course, in case you are asked to find acceleration, you are not asked to calculate the acceleration. But in case you are asked to find acceleration, you can apply Newton's second law for motion in the horizontal direction. So resultant force of the block has magnitude n sin theta. That can be written as m into a. Can substitute n here to find a. So calculation of acceleration actually I have discussed in the past for this case, one of the special cases in Newton's laws of motion. So in the second case, the inclined plane stops. So when the inclined plane stops, the block slides down the inclined plane under the action of gravity and normal reaction force. As I discussed here, only two forces act on the block: weight mg and magnitude of normal reaction. N is the normal reaction force on the block by the inclined plane. That means magnitude of the contact force between the block and the inclined plane is same as the magnitude of normal reaction on the block by the inclined plane if the surfaces in contact are smooth. So in this case, magnitude of normal reaction I have explained, discussed earlier in Newton's laws of motion, will be equal to mg cos theta. That means magnitude of the contact force between the block and the inclined plane when the inclined plane is fixed and smooth will be equal to mg cos theta. So you can divide F1 with F2 now. F1 is mg by cos theta. F2 is mg cos theta. So that will be 1 by cos theta whole square. So you can substitute here theta equal to 37 degrees. Come on, those who want to copy the solution of this problem, come on, start writing the solution, copying the solution. Copy down the solution of the problem. That means second case also can resolve the weight mg into components parallel to the inclined surface and perpendicular to the inclined surface. The component mg cos theta acts perpendicular to the inclined surface. The component mg sin theta acts parallel to the inclined plane. So magnitude of normal reaction in second case will be equal to same as the magnitude of the component mg cos theta because the block has no motion in the direction perpendicular to the inclined surface. So the answer is 25/16. Come on, finish writing. In case you need more time to copy the solution of this problem, take a pause and take your own time. So for question number 40, third option is answer. So look at the next question, question number 41. This I have discussed in one of the special cases as it is the same thing. So you need not discuss it again. Already discussed that the maximum length of the hanging part of the chain for which the chain can remain at rest on the table is given by nu L by nu plus 1 in one of the special cases. So first option is answer for 41. See the question number 42. Body is placed on a rough inclined plane of angle of inclination theta to the horizontal. As the angle is increased from 0 degrees to 2π, the contact force between the block and the plane. So you have to find out how the magnitude of the contact force between the block and the plane change here. This part of this question I have discussed in the question number 33. I have discussed the same discussion in the question number 33. You can see the solution of question number 33. An angle of inclination of the inclined plane is less than the angle of friction between the two surfaces in contact, or angle of repose. And the block will be at rest on the inclined plane. The block is at rest on the inclined plane, on the inclined surface. Then the magnitude of the contact force between the block and the inclined surface, same as the magnitude of the total reaction force on the block by the inclined plane. So you can see the solution of question number 33. All the same discussion I have done in the theory also. The angle of inclination of the inclined plane to the horizontal less than the angle of friction or angle of repose. The block remains at rest on the inclined plane. Then magnitude of the contact force between the block and the inclined plane means same as the magnitude of the total reaction force on the block by the inclined surface, which will be equal to mg, which is independent of angle of inclination of the inclined plane to the horizontal. That means when the angle of inclination to the inclined, when the angle of inclination of the inclined plane to the horizontal, theta is increased from 0 degrees to phi, the magnitude of the contact force of the block and the inclined plane remains constant, equal to the magnitude of its weight mg. But when theta is more than phi, when phi is less than theta, less than 2 phi, or when theta lies between phi and 2 phi, or when theta is more than angle of friction, then the block begins to move down the inclined plane with an acceleration. In that case, magnitude of kinetic friction of the block with the inclined plane will be equal to nu k to magnitude of normal reaction, which is equal to magnitude of normal reaction is equal to mg cos theta. So magnitude of the normal reaction is equal to mg cos theta, magnitude of kinetic friction will be equal to nu k to mg cos theta. So magnitude of the total reaction force or magnitude of the contact force. Magnitude of the contact force is same as the magnitude of total reaction force, that is the resultant of normal reaction and force of kinetic friction. Fk is nu k to n here, n is mg cos theta. So if you substitute Fk equal to nu k into n. So magnitude of the total reaction you get on n into under root of 1 plus nu k squared. Magnitude of normal reaction equal to mg cos theta. So when the angle of inclination theta is more than, when the angle of inclination of the inclined plane to the horizontal is more than the angle of friction between the two surfaces, then magnitude of the total reaction force on the block by the inclined plane during the motion down the rough inclined plane is equal to mg cos theta into root of 1 plus nu k square. So as theta is increased, the value of cos theta decreases. So therefore, the magnitude of total reaction of the block by the inclined plane decreases. That means as the angle of inclination of the inclined plane to the horizontal increases gradually from 0, the magnitude of the contact force between the block and the inclined plane first remains constant until theta reaches the value phi. Then it decreases. If you want to copy down the solution, you can copy down the solution. So for question number 42, which I have just now discussed, second option will be the answer. That means first remains constant and then decreases. So magnitude of the contact force between the block and the inclined plane first remains constant, then decreases. Okay, I will be discussing the solutions of the remaining questions numbering from 43 onwards in my next class.